King in.
Oh, Sandra, hi.
Hi, I am in the right session. I think it's track 1.
I'll be attending your talk.
Oh, okay. Do you know when it is, or is it just?
Yours is track 1, 6th talk.
6 talk, and I'm in the right place.
Yeah.
Okay.
Your
All right,
number
thank you.
54?
50.
Your number 54?
Yeah.
Yes.
6th one.
Thank you.
ഞാൻ ഇന്നലെ ഒരു മെസ്സേജ് അയച്ചിട്ടുണ്ടോ കേട്ടോ?
എന്താ
മെസ്സേജ് അയച്ചല്ലോ
ഏതാ
പ്രസന്റേഷന്റെ.
ആ
ആ.
Hi,
Hello,
Manu.
Sandy.
Just want to say hello to you.
Yeah.
How are you doing?
Pardon?
How are you doing?
Yeah, doing well.
Okay, good.
So you are at home?
I'm at home,
You are
yes.
at home.
Today I'm at home and tomorrow I will be in my office when I will be lecturing.
Hi, Sandy.
Hi, Vijay. Hi.
So how are things there?
Well, not so good. Mostly things are locked down.
Still lockdown now?
Yeah.
I see.
We are teaching online already since October.
Yeah.
How about shops and all that? Are they open or?
Shops are closed except basic shops.
Slovenia.
Yeah, other shops are closed.
So I think okay, our case is better in some sense.
Yeah.
Not better in the sense of spreads, but in the sense of unlock.
Another start it off.
Yes.
Okay, bye.
Bye. See you tomorrow.
See you.
Yeah. I invite Professor Manoj Changat, University of Kerala, Department of Future Studies, to chair the contribute to session part 1. Professor Manoj.
Okay, thank you. So in this session, we have 8 presentations, 8 talks. So I will invite first paper is authored by Jisha Saraswati, Manju Menon, Sadish, and the title of the talk is Co-Secure Domination Number of Generalized Sierpinski Graphs. Who is presenting the paper? Who is presenting the talk?
Sir, me, Jisha Saraswati.
Okay, go ahead. So you are from NSS College, Changanasheri.
Changanasheri. Yes, sir.
Please, go ahead. So you have 15 minutes total.
Yes, sir.
Including discussion.
Okay, sir. So my slides visible?
Yes.
Okay. Good afternoon, everyone. My name is Jisha Saraswati, research scholar from NSS Hindu College, Changanasheri, affiliated to MG University. First of all, I thank the ICNTDM organizers for giving me an opportunity to present my paper. The topic of my presentation is co-secure domination number of generalized Sierpinski graphs. My co-authors, Manju K. Menon, Assistant Professor, St. Paul's College, Kalamasheri, and Satish Ian, Associate Professor, NSS Hindu College, Changanasheri. In this paper, we have obtained the co-secure domination number of Sierpinski graph and an upper bound for the co-secure domination number of generalized Sierpinski graph of paths and cycles. And the bound is sharp in the case of generalized Sierpinski graph of paths. We move on to our first definition, domination number. Let G be a graph with vertex at V and edges at E. S be a subset of V of G. A vertex V dominates itself as well as all the vertices of G that are adjacent to V. Set S is said to be dominating set if each vertex of G is dominated by at least one vertex of S. The cardinality of a minimum dominating set is called the domination number of G, which is denoted by the symbol gamma of G. We make the definition a bit more clear. We'll go through an example. Here it is C4. Here we'll start from the vertex 1. 1 will dominate 2 and 4. So we have to choose one more vertex. So here obviously 1, 3 forms a minimum dominating set. And here the domination number is 2. Now we move on to our second definition, co-secure domination number. Let G be a graph with vertex at V and edges at E. A dominating set S, subset of V, is called a co-secure dominating set. If for each U element of S, there exists V outside the set S such that V is adjacent to U. And at the same time, whenever we interchange U and V, the resulting set should be a dominating set. The cardinality of a minimum co-secure dominating set in G is the co-secure domination number, which is denoted by the symbol gamma CS of G. And the corresponding set is called a gamma CS set. We'll go through first example G1. Here it is given a graph G1. We are going to find the co-secure domination number of G1. We start from the vertex 3 because 3 has a highest order. So we'll start from the vertex 3. 3 will dominate the rest of vertices. But singleton 3 doesn't form a co-secure dominating set because whenever we interchange 3 to 4 or 2 or 1, the resulting set won't be a dominating set. So we have to add one more vertex. If we add 4 along with 3, our set becomes 3, 4, which is also not a co-secure dominating set because for the vertex 4, there doesn't exist any vertex to interchange with 4 because 4 is adjacent to only 3. So we have to choose either 1 or 2. the possible co-secure dominating sets are along with 3 possible. First possibility 1 3 or 2 3. This is the minimum co-secure dominating set, and here the co-secure domination number is 2. We move on to another example. Here it is given a graph G. We'll start finding the co-secure domination number with respect to X or V. If you start from X, X will dominate W, V, U, and Y. So we have to add one more vertex, say Z. So let our set be XZ. Then it forms a dominating set. And at the same time, if we interchange X with W, then our resulting set WZ doesn't form a dominating set. But if we interchange X with V, then the resulting set VZ is a dominating set. So there exists a vertex to interchange with X. And at the same time, we can interchange Z with respect to Y, Z and Y. So our set XZ forms a co-secure dominating set, and it is the minimum set. So the co-secure domination number is 2. Now we move on to our definition of generalized Sierpinski graph. Generalized Sierpinski graph, which is denoted by S of GT, where G denotes the base graph and T denotes the dimension. It is the graph with vertex at V raised to T, where V raised to T is a set of words of size T on alphabet V. The letters of a word U of length T denoted by U1, U2, etc. UT. The adjacency is defined as follows. UV is an edge in S of GT if and only if there exists I satisfying the below 3 conditions. Uj equal to Vj for j less than I, Ui not equal to Vi, and at the same time Ui, Vi should be an edge of the base graph. Uj equal to Vi and Vj equal to Ui for j greater than I. These are the conditions. If we choose our base graph as Kn, then we call the generalized Sierpinski graph as Sierpinski graph. We'll explain the definition using an example. Here it is given, generalized Sierpinski graph of path P8. The base graph chosen is P8, and we are considering the second dimension. Here we can see 8 copies of P8, which are joined using the adjacency. 1, 2 adjacent to 2, 1, 2, 3 adjacent to 3, 2. Here the adjacency definition is Ij adjacent to Ji, even only if I and J are adjacent in P8. That means we cannot make adjacency among 1, 3 and 3, 1. Likewise 1, 4 and 4, 1, because 1 and 3 are not adjacent in P8. This is the example of generalized Sierpinski graph of cycles. Here we chosen the base graph as C4. And we can see the 2 dimension and 3 dimension. In SC43, that is third dimension, we can see the adjacency is 2, 1, 1 adjacent to 1, 2, 2. And 1, 4, 4 adjacent to 4, 1, 1. That is I, J, J, etc. J adjacent to J, I, etc. I, even only if I and J are adjacent in C4. We can view this graph in another way. Consider SC42. We can view this graph as 4 copies of C4, where 4 stands for the number of vertices in C4. 4 copies of C4 connected using the adjacency Ij adjacent to Ji, if and only if I and J are adjacent in C4. Likewise, SC43 can be viewed as 4 copies of SC42, previous dimension, using the adjacency I, J, J, etc. J adjacent to J, I, if and only if I and J are adjacent. In general, if we are given a graph Cn and we are going to find a T dimension, then we can view the graph as n copies of SCn T minus 1. This is the example of Sierpinski graph. Here the base graph is complete graph K3, and we can see the second and third dimensions. Now we move on to our first theorem. In this paper, we are trying to find out the co-secure domination number of generalized Sierpinski graph of complete graph, cycle, and path. First theorem is co-secure domination number of Sierpinski graph. It is found out to be n raised to t minus 1, where n stands for the number of vertices and t stands for the dimension. Second theorem is co-secure domination of generalized Sierpinski graph of paths. We got an upper bound n raised to t minus 1 ceiling function 2n by 5, where ceiling function 2n by 5 is the co-secure domination number of path Pn. Here the bound is sharp, and the equality attains when n equal to 5m. It becomes 5m raised to t minus 1 ceiling function to 5m by 5, that is 2m. Now we move on to the last theorem, co-secure domination number of generalized Sierpinski graph of cycle. We got both lower and upper bound for Cn. Here the lower bound is a bit complex, but it is sharp. Our upper bound is same as that of Pn, n raised to t minus 1 ceiling function 2n by 5. And these are the references. Thank you for the kind attention.
So is there any questions from the audience?
Yeah, I have a quick question. So you have studied co-secure domination in Sierpinski graphs. So there is a dual concept, which is even more basic. It's secure domination. So did you also consider secure domination?
Yes, sir. We have already go through secure domination, and we have presented a paper in the previous ICNTDM. We have found out the secure domination number of generalized Sierpinski graph. And after that, we have selected co-secure domination number. And after studying co-secure domination, we came to know that most of the results of secure domination can be easily derivable using these co-secure domination.
Okay, nice, thank you.
Thank you, sir.
I have the usual question, when is this domination number and secure domination, co-secure domination coincide? Are there any inequalities or class of graphs where equality holds?
Yes, sir. For graphs with minimum degree greater than or equal to 2, the co-secure domination number of that graph is always less than or equal to secure domination number of the graph. For graphs with minimum degree greater than or equal to 2.
Okay. Do you have any special reason for choosing this Sierpinski graphs?
Yeah, that's I want to ask that question.
Or you tried for a graph class?
There is no special reason for this, sir. Actually, there is no special reason, sir.
Okay.
For which classes of graphs this co-secure domination number has been studied?
For generalized Sierpinski graph of Kn, Pn, and Cn.
Only these generalized Sierpinski graphs, this co-secure domination is studied? For no
Yes,
other
sir.
class
For 3 graphs.
No, that's what you studied, but other people studied other classes, right?
Yeah, that's. Okay.
Okay, sir.
Okay, let us thank the speaker.
Thank you, sir. Thank you.
So next, we'll wait or we'll start the next talk, right? The next speaker is ready. It is contributed paper 31.
Yes, sir. May I share the screen, sir?
Yes. This is S.A. Khandekar, S.A. Mane, and Bafare from University of Pune. And the title is One-to-One Conditional Path Covers on Augmented Cubes. So who is presenting?
I'm
Khandekar?
Smita Kandekar, sir.
Shweta Khandekar, okay.
So, am I start, sir?
Yes.
Okay. Good afternoon, all. My name is Smita Kandekar, and I'm assistant professor at Savitribai Phule Pune University, Department of Mathematics. This is joint work with the S.A. Mane and Professor B.N. Bafare. The title of my presentation is One-to-One Conditional Path Cover. Title is One-to-One Conditional Path Cover. So first of all, we will see all the words present in the title, what it mean by that, and then we will go towards the problem. So journey gets start with the interconnection networks. So interconnection networks are the collection of the processors, memory units, which are joined by the links. And you can see in our day-to-day life, there are many systems are there in which interconnection networks are used. Mostly we have seen the parallel systems. Most of the application uses the parallel system to improve the speed and efficiency of the system. And in that one, the study of the underlying interconnection network is very important. We can study the interconnection networks by using the underlying graph, because we can easily see interconnection network we can represent as a graph with the vertex as an processors, and the linkage are nothing but the edges. And that's why it is very easy to see the properties of the interconnection network by using the graph theoretical properties of the corresponding underlying graph. So these are the very popular interconnection networks which are used tremendously in many applications. So among them, we will see the hypercube. So hypercube of order n is graph having the vertex set nothing but the all binary n tuples. So the combinations of zeros and one, and having the n coordinates are there. So we can construct that hypercube recursively. So let us see how we can do that. So hypercube of order one can be constructed in this fashion, having the two vertices joined by an edge. We have to take the two copies of that and then join by the corresponding vertices. So here we have to take 0 0 for the vertices of the one copy, and we have to attach 1 1 for the another. Similarly, we have to take the two copies of the Q2, and then join them, join the corresponding vertices to get the Q3. There are many variations of the hypercube get introduced to represent many graphs, and which are applicable in various fields. Among them, we have this hypercube is n regular, n connected bipancyclic subgraph. Bipancyclic means it contains all even length cycles from the length 4 to the cardinality of the vertex set of that graph. This graph contains 2 raised to n vertices. Among them, whatever the variations are there, one of the richest the variation of the hypercube was given by Chodam and Sunita, that is precisely the augmented cube. And that augmented cube is also recursively constructed. So let us see the construction of that, rather going to through these pictures. So we have to the vertex set of the augmented cube and the hypercube both are the same, that is the binary n tuples. And what we have to do, we have to take the copies. So here AQ1 and Q1 both are same. So augmented cube of order 1 is same as the hypercube of order 1. Then take the two copies of AQ1 and then join them by the corresponding vertices as an hypercube. At the same time, we have to join each vertex to its complement. So that is what the new thing. So at every stage, we have to add the two edges for the every vertex. So this 0 1 has the complement 1 0. So the same thing, we have to take the two copies of AQ2 and then join the corresponding vertices and then join the the complements. So you can see every vertex has unique. So if I say this vertex U, then it has unique hypercubic neighbor, because we have joined it by this hypercubic edge, and also it has unique complement. Okay, so it is joined by this complementary edge. So every vertex has these two neighbors which will play a very important role. Now, if you see the interconnection networks, there is very central issue is to find out the disjoint path, vertex disjoint path, which are very useful to run the things parallelly at a time. So that is that will increase the speed of the network. And That's why the study of the disjoint path in the interconnection network is very important. There are three types of the disjoint paths are there. One-to-one, in which we have one sink and one source and one sink. And in between we will find out the node disjoint path. Then we have one-to-many, means we have one source and we have many sinks are there, and in between them we will find out the disjoint path. Similarly, we have many to many. So many sinks are there, many sources are there, and we will find out the disjoint path among them. Now, if when we find out this disjoint path, so among them or along them, if all the graph will get covered, then we call that as disjoint path cover. So it contains all the vertices of the graph, and it is very important because we are including all the processors in our whatever the present in the system in our application. So disjoint path cover concept we have. Now here what we have one-to-one what the disjoint path cover we have, but how many path it contains? So in between two vertices we have the path. That path may be two path, three number of paths, okay, which will cover all the vertices. So that number will decide this new concept, that is what the MDPCable graph. That means M disjoint path cover. So whenever in between any two pair of vertices, so U and V, what we have, if you have m number of paths in between them, which will cover all the vertices of the graph, we call that graph as MDCBable graph. Okay, so that M vary from 1 to the connectivity of G. So if it is 1 DPCable, means we get a Hamiltonian path in that graph. If it is 2 DPCable, means we get a Hamiltonian cycle in that graph, and so on. Now note that finding this one-to-one, one-to-many, many-to-many MDPCable path in a given any graph is an NP-complete problem. So we are looking for this problem for the class augmented cube. But now augmented cube, it is already shown that augmented cube is MDPCable from 1 to the connectivity of the augmented cube. Augmented cube is 2n minus regular, 2n minus connected graph. So it is what almost double the connectivity than the hypercube is there. And one of the feature of this augmented cube is it is pancyclic, means it contains all length of cycles from odd and even both. So we have that which will be useful for proving the results. Now here we are considering, so once it is already proved that it is MDPCable, but now if I place some condition with that, okay, if my MDPC, that is the disjoint path cover, satisfy some condition, okay, then we said that MDPC as a conditional MDPC. Okay, so we have considered this problem. So conditionally MDPCable graph we have chosen here. Why we have used that? Because in many applications what's happened, we required we have the processors, so some of the processors may conflict, okay, whenever they are present on the same path. So to avoid that confliction, or they are redundant, so to avoid that thing, we always have to design the interconnection network in which that particular two processors should be on the different path always. So whether if you require the 3 DPC, if you require the 100 DPC, whatever the connectivity of that graph is there, less than that. But in that every MDPC, you should want that particular processor should be what kept on the place where they lie on the different path. So that is what the problem. So you can see in our home also, whenever we have the many home appliances are there, so they are rather placed on the parallel networks, okay, they are not on the series. So there are many results are there, many authors proved studied this path cover things. So many to many path covers are what obtained in hypercubes, in the faulty hypercubes, in the faulted hypercubes, in the cylindrical tortoise grids in KN cube. Lee and etc. proved the existence of the one-to-one disjoint path cover in the multi-dimensional tool, right? Then Shi and Cow, they have given the one-to-one disjoint path covers in KN cube. Similarly, you and this Hung gave us the existence of the one-to-one disjoint path covers in alternating group path and in augmented cube. Now this Hung has given the existence of many to many path cover, in which what we have two sinks and two source, and whatever the two paths vertex disjoint path he has find out, that contains the equal number of vertices. That's why it is called as a two equal path cover. So this result we have used to prove our result. We have gave the condition that these two vertices particular which will be redundant, okay, we will place that on the two position which are very special, that is W and its complement, okay. So we have considered this case. So what we have proved in this AQN in augmented cube, we have find out MDPC, that is M disjoint path cover in between U and V, such that that W is present, which is other than this U and W, and of course their complements, okay, such that what's happened, W and its complement always lie on the different path, and this is true for every M from 2 to 2n minus 1. So that is what the result we have proved. Now, to prove that result, we required this lemma. So using this lemma, there are 16 cases are there, and among that cases, so many cases we required this lemma to prove our result. So these are the some of the cases where the existence of these points make a crucial role when we find out the result. Now we can extend our problem, okay, to why only two vertices. So if you take L vertices, W1, W2, Wn, okay, which are of course other than V complement and U complement and V complement, whether there exists a T path cover in between U and V, such that Wi and W complement, they always lie on the different path. So that is what the extension of this problem that is we are studying. And also here we are seeing this W, we are talking about W and its complement always. So why only W and its complement? So we can see another version of this problem also. So for every four tuple U, V and W and Z now. Now Z is different from W complement, okay. So these two vertices other than the complement of U and V, there exists MDPC in between. So whether there exists, so that is what the question, sorry, whether there exists MDPC in between U and V such that W and that Z on different path. It is more general, and we are studying these two problems now. So this is these are the references which we have used.
Okay, any questions? Any questions, please? No questions. So is there, from your results, is there any algorithmic implications? Can you construct?
Actually, we have constructed the basic case AQ4 to prove that basic case. We have used actually the program algorithm, but it is very difficult to extend that to the higher dimensional augmented cube. So we are trying actually in this paper we have given the existence. So we have not that type of step by step to go algorithmic.
But your proof approach is constructive, right?
Yes, yes.
So that's why I asked. Okay. So let us thank the speaker.
Thank you, sir. Thank you for learning this. Okay, thank you, sir.
So we go to the next paper. Is by Sarada Nilyanayaki and Lourdes Swami. Okay.
Good afternoon, sir. Good afternoon, sir. Am I audible?
Yeah. Your paper
yes,
is
shall I?
How is conjecture on product of shadow graphs of paths?
Yes, sir.
Yes, please.
Yes, sir. I'm sharing my screen, sir.
Yes.
Good afternoon, at all. I'm very happy to present a paper in ICNTDM 2020. So the title of my paper is Heskowski's conjecture on product of shadow graph of paths. Myself, Sharada Nilyanayaki, working as an assistant shadow graph of paths. The outline of my presentation is preliminary definitions of graph pebbling conjectures, and followed by the main results which we are proving in this presentation is followed by the references. So graph pebbling is the mathematical game and area of interest placed on the graph with pebbles on the vertices. The graph pebbling was first suggested by Harris and Sachs for solving a problem, but in 1989, Chung introduced the concept in the literature. So for the basic is the pebbling move. So for considering a pebbling move, we are supposed to consider a connected graph with fixed number of pebbles on it. So a pebbling move is an operation is a removal of two pebbles from a vertex and a removal of two pebbles from a vertex and placing on one pebble to an adjacent vertex. So this is a pebbling move before moving and this is after moving. So the basic important definition of pebbling is the pebbling number is the small. That is, by using this pebbling moves repeatedly, we should able to reach any vertex. So that the smallest number is called the pebbling number of a vertex, and the pebbling number of a graph is the maximum for all, considering all the vertices in the graph. So this is the pebbling number. This was generalized as T pebbling number by Lourdes Swami, who is our guide. If the T pebbling number is the same as, however, the distribution of Ft of G pebbles on the vertices of the graph, we can able to reach any specified target vertex by a sequence of pebbling moves. It was denoted by Ft of G. The next important concept is pebbling related definitions, that is two pebbling property and 2T pebbling property. Two pebbling property was introduced by Chung. So in the two pebbling property, if it is possible to move two pebbles to any target, any specified target vertex, whenever P plus Q is greater than 2F of G. That is, if P plus Q is greater than 2F of G, then we can move two pebbles to any target vertex, where P is the number of pebbles on the distribution and Q is the number of occupied vertex. This was generalized as 2T pebbling property by Dr. Lourdes Swami. That is, the condition is P plus Q is greater than 2Ft of G pebbles. If this inequality is satisfied, then we can move 2T pebbles to any target vertex. Then we can say that the graph satisfies two pebbling property. The next one is important conjectures in graph pebbling. There are three conjectures. The first conjecture was proposed by Chung. So in his paper, it was due to Graham. Therefore, we can call that as Graham's conjecture. The conjecture shows that the pebbling number of the graph G cross H, that is the product graph G cross H, is less than or equal to the pebbling number of the first graph into the pebbling number of the second graph. So these are the literary survey for the first conjecture. It was generalized as Lourdes Swami's conjecture, and the conjecture shows that the T pebbling number of the product graph G cross H is less than or equal to the pebbling number of the first graph into the T pebbling number of the second graph. So these are the evidences that this conjecture is true. Since it contains T pebbling number, so we can call this conjecture as also T pebbling conjecture. Then this conjecture was further generalized as Heskovsky's conjecture, and the conjecture states that the ST Pebbling number of the product graph G cross H is less than or equal to the S Pebbling number of the first graph into the T Pebbling number of the second graph, where G and H are any connected graphs and S and T are any integers. So so these are the literary survey for this conjecture. Okay, so now in this presentation, I'm going to show that this conjecture is true for the product of shadow graph of path. So before that, we can go for the definition of shadow graph of path. So a shadow graph of a graph G is, we can take two copies of G, naming G1 and G2, and also having the edges as each vertex U in G1 to the neighbors of the corresponding vertex V in G2. So in addition to the vertices and edges on G1 and G2, we are having these edges in the shadow graph. So I'm taking the shadow graph of path. So I'm taking two copies of a path. This is just an illustration for the graph. So I'm taking the two copies of the path. So I'm connecting this naming x1, x2 and up to xn. So x1, x2, xn, and they are taking another copy of pn, that is xn plus 1 to x2n. So this graph contains 2n vertices and the edges as shown in the figure. That is, the neighbor of x1 is connected to the copy. So x5 is connected to x2. So the neighbor of x2 is x1 and x3. So the point x6 will be connected to x1 and x6. So for this graph, the preliminary results I am using that. So Ludusamy et al. Proved that these are all true. Myself and Ludusamy have proved these results, and we have published in various journals. So the Pebbling number of this graph is 2 power n minus 1 plus 2, and T Pebbling number is shown here, and we show that this graph satisfies two, and I have shown that this graph satisfies, that is the product of the shadow graph cross any graph. This graph satisfies two Pebbling property. Then this graph satisfies Graham's conjecture. This was proved in number 6, and in number 8 we have proved that this graph satisfies T Pebbling that is T Pebbling conjecture. In other words, we can say that it is Ludesamy's conjecture. So now we are proving that this conjecture is true. This product graph is true for Heskovsky's conjecture. That is, Pn cross Gn is less than or equal to the S Pebbling number of the first graph. That is, the S Pebbling number is S into 2 power n minus 1 plus 2 into Ft of G. So we can put this much of pebbles to our graph, and we can show that we can able to move St pebbles to any target vertex. So this we can prove. So here I am having an illustration of D2 of Pn cross G. G is any graph which satisfies 2T Pebbling property. So I am taking the circles in show that this is just an illustration. This G is any graph. This G I am taking. So here 8. So P4 I am taking. So here we are having 8 copies of G. That is x1 cross G, x2 cross G, x3 cross G. Similarly, x8 of G. So the proof is by induction on S. When S is equal to 1, we can see that here if we put S is equal to 1, then the result follows from the Ludesamy's conjecture. So S is equal to 1. The proof is on induction. So S is equal to 1. It follows Ludesamy's conjecture. For S is equal to 2. So we can have 2 into 2 power n minus 1 plus 2 into Ft of G pebbles on the vertices of the graph. So we can have the proof like this. So if this particular copy contains 4 Ft of G pebbles, then we can move 2 Ft to this copy, and then Ft pebbles to this copy. Then Ft pebbles, Ft of G pebbles will be contained in this copy. By that we can have T pebbles to any target vertices. Okay. So the remaining number of pebbles will be distributed on these copies, and we can move by induction S minus 1 into T pebbles from these copies. Already we have moved T pebbles. Now we can move S minus 1 into T. Therefore, we can move ST pebbles. Like the similar way, there are 2 more cases. Here I have said that this copy contains 4 Ft of G pebbles. Suppose if it contains less than 4 and it lies between 2 Ft to 4 Ft, there will be a case. And if it is less than 2ft, then there will be a case. So in the both cases, we can take a path. So here I'm having this a path like this and a path. So these two disjoint paths I have shown here. So by this path we can move. Anyhow, we can move ST pebbles to the target vertices. So we can say that ST of D2 of Pn cross G is less than or equal to S into 2 power n minus 1 plus 2 into Ft of G by induction on S. So thus proving this result, we can have these results as corollary, since we know that Pn, the path satisfies 2T pebbling property. So as we have stated in the result that a G is any graph satisfies 2T pebbling property, the result is true. Here we have shown that shown as corollary that since a path satisfies 2T pebbling property, complete graph satisfies 2T pebbling property, cycle satisfies 2T pebbling property, star graph satisfies 2T pebbling property, fan graph satisfies 2T pebbling property, and the graph which we are having itself satisfies 2T pebbling property. That is, so D2 of Pn cross D2 of Pn. So we can say that this is the ST pebbling number. So this is the upper bound of ST pebbling number of a graph. Thus, in the Heskowitz conjecture, if G is a shadow graph of such as any graph which satisfies 2T pebbling property, Heskowitz conjecture is true. So we can have an open question that if satisfies means what will be the result. That is the first on this graph pebbling area. So these are the references I have made for giving the results. Thank you.
Any questions? No questions? So which product you are considering? Cartesian product?
Yes, sir. Cartesian product.
Okay, there is no questions. Let us thank the speaker.
Okay, excuse me.
Thank
Yes.
you.
There is an announcement.
Thank you very much, sir. Thank you for this great opportunity.
Yeah, please.
Yeah, Mr. Purushottama, abstract number 18. He should go to track 2. Purushottama, abstract number 18. He is present in this track.
No.
Yeah.
He is not presenting.
No, he is not presenting, but he is present here. So he should present in track 2.
But he is not presenting in this track 1. There is no 18.
No, Purushottama is attending there.
Okay.
You should move to track 1.
Track 2.
Sorry, track 2.
Okay.
Purushottama, did you hear? Proceed. Yeah.
Okay. So let us, the next speaker, next paper is by Manali Sharma and Praveen Garg. And the paper title is Some Properties of Extended Transformation Graph of a Graph. Please, you're there from the University of Rajasthan, Department of Mathematics. Please.
Good afternoon, sir. My name is Manali Sharma. I am from University of Rajasthan. I am presenting paper on some properties of extended transformation graph of a graph. Thank you for giving me the opportunity to present the paper. Here is the definition of transformation graph. Transformation graph is G, x1, x2, x3. Here the vertex set is V union E and edge set as follows. If Vi, Vj belongs to V and Vi and Vj are adjacent in G, then x1 has sign plus. And if they are not adjacent in G, then x1 has sign minus. Similarly, if Vi and Vj belongs to E, if they are adjacent, then x2 has sign plus, otherwise it has sign minus. If Vi belongs to V and Vj belongs to E and Vj is incident at Vi in G, then x3 has sign plus, otherwise it has sign minus. Now we introduce notion of extended transformation graph. Here the vertex set is V union E bar. Now for the edge set, x1, x2, x3 are same as in the transformation graph. Now if Vi and Vj belongs to E bar then Vi and Vj are adjacent in G bar, then X4 has sign plus, otherwise it has sign minus. If Vi belongs to V, Vj belongs to E bar, then Vj is incident at Vi in G bar, then X5 has sign plus, otherwise it has sign minus. If Vi belongs to V and Vj belongs to E bar, then Vi and Vj are adjacent in Kn, then X6 has sign plus, otherwise it has sign minus. Now, here is the figure for extended transformation graph when all the sign are plus, and other figure is for extended transformation graph G plus minus 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 minus. Now here are some observation. First is the definition of extended transformation graph when all have sign plus. Now next observation is that if vertex set of first extended transformation graph can be partitioned into G and LKN, line graph of complete graph, and the vertex set of other extended transformation graph can be partitioned in G and complement of line graph of complete graph. We will use notations Vi and Vij. Vi belongs to V and Vij belongs to E union E bar. Here we define two operations, +1 and +2. +1 means when V is the vertex at V1 union V2 and E is equal to E1 union E2 union E3, that E3 is Vi Vij. And +2 sign if E3 Vi Vij, if Vij belongs to E1, Vi Vjk if Vjk belongs to E1 bar. Now here are two lemmas. The first extended transformation graph is isomorphic to G plus 1 line graph of complete graph. And the next extended transformation graph is isomorphic to G plus 2 LKN bar. Now, application of these two lemmas can be seen in the theorems. Now, the first proposition is that the first extended transformation graph has vertex at n plus 1 C2 and edges as m plus n square n minus 1 by 2. And the next extended transformation graph has number of vertices n plus 1 C2 and number of edges 5 minus nm plus n plus 1 n minus 1 n minus 2 by 8. Now next theorem is the extended transformation graph GE when all have sign plus of a graph G is Hamiltonian graph for all G except the empty graph on two vertices. Here is the proof of the theorem. First, we consider the Hamiltonian cycle in Kn. Now, since line graph of Hamiltonian graph is Hamiltonian, so we consider the Hamiltonian cycle in line graph of complete graph. Now, we extend this Hamiltonian cycle of line graph of complete graph to include the vertices of G. In this way, we get the proof. Now, next theorem, the next extended transformation graph for GE plus minus minus minus. Let the G be a graph of n vertices, m edges, vertex at Vi. Each vertex Vi has degree di, and di is greater than equal to 6n minus 10 by 4. Any two non-adjacent vertices Vi and Vj has di plus dj greater than equal to n square minus 3n plus 8 by 2. Then the extended transformation graph is Hamiltonian for n greater than 8. For the proof of the theorem, we use the Orr's theorem. First, we see the degree of the vertices in the extended transformation graph. The vertex Vi has the degree 3 di minus m plus n minus 2 n minus 1 by 2, and the degree of vertex Vij is n minus 2 by 2 if Vi and Vj is edge. If Vi and Vj is not edge, then the degree is n minus 2 C2 plus n minus 2. Now, from the Orr's theorem, for n greater than equal to 3, if di plus dj greater than equal to n, for every pair of distinct non-adjacent vertices Vi and Vj of G, then G is Hamiltonian. Now, according to non-adjacent vertices, we have the following cases. We have first case for Vi and Vj belongs to V. Then we apply the Orr's theorem and we get the result di plus dj is greater than equal to n square minus 3n plus 8 by 2. Now for case 2, if Vi belongs to V and Vjk belongs to vertex set of complement of line graph of complete graph, then we have two subcases. For first subcase, if Vi and Vjk are not adjacent and Vk is edge, then we apply the Orr's theorem and we get the result di is greater than equal to 6n minus 10 by 4. For For next subcase, we apply same in the similar way. Vi and Vj are not adjacent and Vi Vj is non-edge here. Then after applying Gauss theorem, we get the result di is greater than equal to 2n minus 1 by 4. Now for case 3, if both the vertices are from complement of line graph of complete graph, then we have 3 subcases. For the first subcase, we get the result after applying Gauss theorem that the result is true for n greater than 8. For next subcase, the result is true for n greater than 7. And for next third subcase, we get the result for n greater than 6. So in this way, we get the desired result. Now the next theorem, the extended transformation graph when all have sign plus is Eulerian if and only if any of the following condition hold. First condition, mod of Vg is even and degree of each vertex in G is odd. And second condition, mod of Vg is odd and degree of each vertex in G is even. For the proof of this theorem, since degree of Vij is 2n minus 2, here the degree is already even and degree of Vi in the extended transformation graph is equal to degree of Vi in G plus n minus 1. So for this degree to be even, if mod of Vg is even, then n minus 1 is odd. Therefore, degree of Vi in G should be odd. Similarly, for degree of Vi in extended transformation graph to be even, if mod of Vg is odd, then the degree of each vertex in G should be even. Now, Eulerian theorem for the extended transformation graph G plus minus plus minus minus minus. For this, let G be graph of n vertices, m edges, vertex at Vi. Vertex Vi has degree di, then the graph is Eulerian if and only if following conditions hold. N is even. Second, 3di minus m plus n minus 2 n minus 1 by 2 is even. Third condition, n minus 2 C2 is even. For the proof of the theorem, we have already seen the degrees in these extended transformation graph. Now, the first part is obvious proof. For the converse part, if n is odd, then n minus 2 C2 can either be even or odd. If n is odd and n minus 2 C2 is odd, then degree of vertex Vij corresponding to edge Vi Vj in extended transformation graph is odd. If n is odd and n minus 2 C2 is even, then degree of vertex Vij corresponding to non-edge Vi Vj in extended transformation graph is odd. Therefore, n cannot be odd. If n is even, then n minus 2 C2 can either be even or odd. If n is even and n minus 2 C2 is odd, then degree of vertex Vij in extended transformation graph is odd. Therefore, n degree of Vi in extended transformation graph and n minus 2 C2 should be even. So we get the three conditions. Next theorem, let G be a graph of n vertices and then domination number of the extended transformation graph G and all have sign plus for any graph G is ceiling function n by 2. For proof of this theorem by greedy algorithm, it can already be clearly be seen that domination number of extended transformation graph is ceiling function n by 2. Now to prove that ceiling function n by 2 minus 1 is not the domination number. The vertices for domination number are V12, V34, V56. Only these vertices can be chosen since these vertices have maximum degree and are not non-adjacent. So they cover maximum vertices. Now the vertices covered by ceiling function n by 2 minus 1. So all the vertices are 2n minus 1, ceiling function n by 2 minus 1, minus 4, 1 plus 2, up to n, ceiling function n by 2 minus 2. Now to prove that ceiling function n by 2 minus 1 is not domination number, we have to show that all the vertices in extended transformation graph is greater than all the vertices covered by ceiling function n by 2 minus 1 vertices. So we have two cases for n is even and n is odd and we get the result. Now next theorem, let G be a graph of n vertices, m edges, gamma domination number, then consider the following cases. Case 1, if gamma is 1, then we have subcases as follows. First subcase, if G is isomorphic to K1 n minus 1 star graph, then the domination number is 1. If G is not isomorphic to K1 n minus 1, then we have other subcases. First subcase, If G has at least one pendant vertex, then the domination number is 2. If G has no pendant vertex, then domination number is 2 or 3. Second case, if domination number is 2, then domination number of extended transformation graph is less than equal to minimum of 5, n minus n plus 5, except G is K1 union K1. And case 3, if gamma is greater than 2, then domination number of G plus minus the extended transformation graph is less than equal to minimum of 5, n 2 gamma plus m minus n. Case 4, if we have two non-adjacent non-edges, then domination number of extended transformation graph is less than equal to 3 for n greater than equal to 6. For the proof of the theorem, we use the lemma. Now, for the case 1, if gamma is 1, then we divide into two subcases. If G is isomorphic to K1n star graph, let the dominant vertex is Vi. Then the Vi is dominant vertex for the extended transformation graph when G is K1n. For next subcase, if G is not isomorphic to K1n, then we have the subcases based on the number of pendant vertices. If there is at least one pendant vertex, then the dominant vertex Vi and the vertex Vij are the dominant vertices of the extended transformation graph. So we have domination number 2. And for the other subcase, we have dominant vertices as Vi, Vij, and Vj. So or the dominant vertices can be Vi and Vij. So the domination number is 2 or 3. If gamma is greater than 2, then domination number of extended transformation graph is less than equal to gamma plus m minus n minus gamma. Since as gamma vertices of G dominates all vertices of G in extended transformation graph, all non-edges, all edges adjacent to gamma vertices. Now to include rest of the edges, we add E vertices. By adding E vertices, we again include at least n minus gamma vertices. So we subtract n minus gamma vertices. And if gamma greater than 2, then the domination number of extended transformation graph is less than equal to 2 gamma plus m minus n. If Vi, Vj is non-adjacent and greater than 5, then we have dominating set as Vi, Vj, Vij, Vkl, Vmn. We have also the vertex set of G of n vertices as dominant set of extended transformation graph. So the domination number is less than equal to minimum 5, n 2 gamma plus m minus n. Now if gamma is equal to 2, then the domination number is less than equal to minimum of 5, n plus m minus n plus 5. We get this proof from the above gamma greater than 2 result. Let G have two non-adjacent non-edges Vij and Vkl and greater than equal to 5. Then domination set of extended transformation graph is Vij, Vkl and Vmn. So the domination number is less than equal to 3 for n greater than equal to 6. The vertex cover number. Now next theorem, the vertex cover number of extended transformation graph when all have sign plus for empty graph G is n minus 1 n by 2. Let G be empty graph with vertex set V1, V2, Vn. Now vertex set V1, V2 up to all the vertex set of this extended transformation graph, since there is a clip of size n from each vertex of the vertex set. So for vertex 1, we have click V1, V1 to Vn is formed. Now vertex cover number for complete graph of n vertex is n minus 1. Therefore, for its vertex cover, we choose n minus 1 vertices. Now we choose for the vertex V2 and keep continuing, we get the desired result. Now we have the corollary, the independence number alpha of extended transformation graph for empty graph G is n. And we have other corollary, the vertex cover number of extended transformation graph is at least n minus n by 2 and independence number is at most n. Now we have some graph equations. Now first theorem is for any two graph G1, G2, the equation extended transformation graph when all have sign plus G1 is isomorphic to extended transformation graph when all have sign plus G2 holds if and only if G1 is isomorphic to G2. For the proof, if G1 is isomorphic to
Time is, you have just 1 minute. You may skip the proof, I think. It's okay.
Now we have the next theorem. Let K be a complete graph on n vertices with partition n as n equal to n1 plus n2 up to np. Then LG is isomorphic to GE plus left sign plus of H if and only if G is isomorphic to Kn union A1 union A2 up to AK, where A1 is a vertex which is adjacent to n1 number of vertices, A2 is a vertex which is adjacent to another n2 number of vertices, AK is vertex which is adjacent to net rest nk number of vertices of Kn, and H is this disjoint graph of Kni. Here is the proof.
If you skip the proof, you have no time.
Yes, sir. Here are some more graph equations. These are the activities. Thank you.
Okay, any questions? What is the motivation of studying this extended transformation graph?
Sir, actually, the first extended transformation graph follows semi-complete property, and which is useful in defense problems. And further, TGO topology also introduced. So we can explore this work in future.
Okay. So if there is no questions, other questions, we'll just thank the speaker. Okay, so we go to the next paper. This is paper number 53. This is by Tijo James, and the title is Measles-Skin graphs with small gain domination number. Tijo, please.
Yes, sir.
Go ahead. Yeah.
Is my screen visible, sir?
Screen, you make it big, full screen. Yeah, now it's fine.
Thank you, sir. Good evening, one and all. First, I thank the organizers for giving me the opportunity to present my work here. Title of my topic is Measles-Skin of graphs with a small game domination number. First is the well-known definition of domination number. It already discussed here in the first talk. In 2010, Bosjan Broussard, Sandy Closer, and Douglas Afral introduced a game variant of graph domination. This is a game played on a finite undirected graph G, consists of two players, dominator and staller, who alternately taking turns choosing a vertex from G, such that whenever a vertex is chosen by either player, at least one additional vertex is dominated. Here, both players have a conflicting interest. Dominator uses a strategy to dominate the graph in as few steps as possible, and staller uses a strategy to delay the process as much as possible. There are two variants of this game depending on who moves first. If dominator has the first move, we call it as a D game, and if staller has the first move, we call it as S game. The game domination number is the number of vertices chosen in a D game when both players play optimally, and is denoted by gamma G of G. The staller start game domination number is the number of vertices chosen in an S game when both players play optimally, and is denoted by gamma G dash of G. Now I describe D game on this graph P3 Corona K1. dominator has the first move in a D game, and his aim is to dominate the graph in as few steps as possible. So he chooses this vertex. The aim of Stoller is to delay the process. So she chooses one of the undominated vertices. There are one more undominated vertex is there. So dominator chooses that vertex, and the game domination number is 3. Now I describe S game in the same graph, P3 Corona K1. We know that Stoller has first move in the S game, and the aim of Stoller is to dominate the graph with as many moves as possible. So she chooses this vertex, and because of dominated strategy, dominator use any one of the 4 remaining undominated vertices. For example, dominator choose this vertex. This center vertex is also a legal move for both players because this vertex dominates this new vertex. So Stoller choose this vertex, and one more vertex is there undominated. So one more move is needed to finish this game. So gamma G dash of P3 Corona K1 is 4. Now I move on to a short survey of this game. The difference between gamma G of G and gamma G dash of G is at most 1. Also, Bose-Broussard, Sandy-Closer, and Douglas et al. Proved that game domination number is bounded in terms of domination number. That is, gamma G less than or equal to gamma G of G less than or equal to 2 gamma G minus 1. Also, for any k greater than or equal to 1, there exists a graph G with gamma G is equal to k and gamma G of G is equal to k plus r. 0 less than or equal to r less than or equal to k minus 1. Graph G realizes a pair KL if gamma G of G is equal to k and gamma G dash of G is equal to L. Possible realizable pairs are studied in these papers. The only possible realizable pairs are of the form k, k minus 1, k, k, and k, k plus 1. Game domination number is also bounded in terms of order of the graph. Sisla proved that if F is an n vertex forest without isolated vertices, then gamma G of F less than or equal to 5n by 8 and gamma G dash of F less than or equal to 5n plus 2 by 8. Recently, she generalized this result. If G is an n vertex graph without isolated vertices, then gamma G of G less than or equal to 5n by 8 and gamma G dash of G less than or equal to 5n plus 2 by 8. These are 2 well-known conjectures in this area. This is posed by Kinnersley, West, and Samani. Conjecture 1 is in the following way. If F is an n vertex forest without isolated vertices, then gamma G of F less than or equal to 3n by 5 and gamma G dash of F less than or equal to 3n plus 2 by 5. Next is known as 3/5 conjecture. If G is an isolate free n vertex graph, then gamma G of G less than or equal to 3n by 5 and gamma G dash of G less than or equal to 3n plus 2 by 5. Progress towards this conjecture. This conjecture holds for isolate free forest in which each component is a caterpillar. Caterpillar is a tree in which the non-leaf vertices form a path. Sisla proved that if F is an n vertex isolate free forest in which no 2 leaves are at distance 4, then gamma G of F less than or equal to 3n by 5. SK1 tree means subdivision graph of K1 tree. Weakly SK1 tree free forest means isolate free forest F that does not contain SK1 tree whose leaves are leaves in F. Schmidt proved that if F is an n vertex weakly SK1 tree free forest, then gamma G of F less than or equal to 3n by 5. In 2016, Marcus and Peeler claimed that they proved conjecture 1, but they are not yet published it in a journal. Henning Kinnersley proved that if G is an n vertex graph and delta G greater than or equal to 2, then gamma G of G less than or equal to 3n by 5. That means this proves the conjecture for all graphs with the minimum degree at least 2. Sisla provide a better upper bound in the case of minimum degree at least 3. If G is an n vertex graph and delta G greater than or equal to 3, then gamma G of G less than or equal to 0.5574 n. Next is our results in Mislinsky graph. In a search for triangle-free graphs with arbitrary large chromatic number, Mislinsky developed an interesting graph transformation called Mislinsky of a graph. This is the definition of Mislinsky of a graph. For a graph G is equal to VE, the Misled skin of G is the graph mu G with the vertex set V union V dash union W, where V dash is the copy of V, and edge set is the edge set of G together with the U V dash UV belongs to E union V dash W V dash belongs to V dash. The vertex V dash is called the tin of the vertex V and vice versa. The vertex W is called the root of mu G. This is an example of Misled skin of C6. These are our main results. Game domination number of Misled skin of a graph is bounded in terms of domination number of that graph. That is 1 plus gamma G less than or equal to gamma G mu G less than or equal to 2 gamma G plus 1. Also, Stoller-Start game domination number is also bounded in terms of domination number. That is 1 plus gamma G less than or equal to gamma G dash mu G less than or equal to 2 gamma G plus 2. Also, game domination number of Misled skin of G is bounded in terms of game domination number of that graph. That is gamma G of G less than or equal to gamma G mu of G less than or equal to 2 gamma G plus 1. Also, Stoller-Start gain domination number of Misled skin of a graph G is bounded in terms of Stoller-Start gain domination number of G. That is gamma G dash of G less than or equal to gamma G dash of mu G less than or equal to 2 gamma G dash of G plus 2. We have a lemma: if G is a graph with at least 2 vertices, then gamma G mu G greater than 2. So we move on to a theorem. For any graph G, gamma G mu G is equal to gamma G mu G is equal to 2 if and only if G isomorphic to K1. If G is a graph with at least 2 non-adjacent vertices, then gamma G dash mu G greater than 2. We have a theorem: for any graph G, gamma G dash mu G is equal to 2 if and only if G is isomorphic to Kn. If either G is a disconnected graph having at least 3 components or a disconnected graph having at least 1 edge, then gamma G mu G greater than 3. So we have a theorem: for any disconnected graph G, gamma G mu G is equal to 3 if and only if G is isomorphic to K1. Also, if gamma G mu G is equal to 3 for a connected graph G, then there exists a vertex U belongs to vertex set of G such that eccentricity of U less than or equal to 2. And we have a theorem: for any connected graph G with at least 2 vertices, gamma G mu G is equal to 3 if and only if every vertex of G lies in a connected dominating set of order 2. And also we have a lemma: if G is a disconnected graph, then gamma G dash of mu G greater than or equal to 4. Also, if delta G less than n minus 1 for a connected graph G, then gamma G dash mu G greater than or equal to 4. And we have a theorem: for any graph G with at least 2 vertices, gamma G dash mu G is equal to 3 if and only if G not equal to Kn and maximum vertex degree is equal to n minus 1. Thank you.
Okay, any questions?
I have just a short comment for Tijo. So in one of the results, so when you have the game domination number 3, you considered connected domination sets. So I think it might be interesting also to extend your research to connected domination game on Michilsky graphs, because this would be the starting point, this thing, yeah?
Okay, sir.
You know the connected domination game, yes? You just, it's the same?
Yes.
Okay.
Yes.
So it might be interesting to have a look also what this comes out.
Thank you, sir.
Just a comment.
Thank you, sir. Thank you.
Okay, thank you. Thank you, Sanjay. So let us thank, is there any other questions? The audience? So if there is no questions, let us thank Tijo for his presentation.
Thank you, sir. Thank you.
So the next speaker is Sandra Kingen, and the title is Splitters and Decomposers for Binary Matroids. Sandra. Sandra Kingan from Brooklyn.
I don't think you could hear me. I forgot to turn on my speaker. So let me share my screen again. And now I think you can hear me.
Yes, yes.
Yes, okay, good. So thank you to the organizers for this opportunity. My talk today is on matroids. It's not the first matroid talk. I believe yesterday there was a talk on codes, and error correcting codes is also matroids. So today I will talk on splitters and decomposers. So there's a theme that runs across many areas of mathematics. We try to take a large object and break it down into a smaller, more understandable object. For example, you take a large number, and if it's not prime, you try to write the prime factorization of the number. You take a polynomial, you factor it. You take matrices and you try and factor it. For example, you do an LU factorization, or you try to diagonalize a symmetric matrix. And it's the same thing here in graphs and matroids. You take large excluded minor classes and try and decompose it into smaller, more understandable pieces. So the learning curve for matroids is rather steep. It's a generalization of graph theory. And oftentimes we can sort of get by just looking at graphs. And as we see on this slide, so if you consider a graph, here's a graph. The vertices are labeled and the edges are also labeled. The rank of a graph is the size of its spanning tree. This one has spanning tree size 1, 2, 3, and 4. And as you know, the spanning tree is one less than the number of vertices. So if we can write this graph as an incidence matrix like this, and not all 0, 1 matrices can be represented as a 0, 1 matrix of a graph. Some can. So a graph is a special kind of 0, 1 matrix. A binary matroid is any 0, 1 matrix. So that's the objects that we're talking about today, binary matroids. And since it's just matroids over the Galois field F2, 0, 1 matrices, we can kind of get by without the full definition of matroids, because that would take 15 minutes right there to understand. So a graph is a substructure of the complete graph, and the size of the complete graph is n choose 2. A simple binary matroid, simple just means that no repetitions of columns, and is a substructure of the rank R binary projective geometry. So we moved from talking about graphs to geometries, and that's what matroids are. They're a kind of combinatorial geometry. So I'm talking about substructures of these matrices, and they are exponential in size. So the largest graph was polynomial in size, the largest binary matroids are exponential in size. So I need one definition to get started, and that is of a minor. A minor is obtained by deleting edges and contracting edges. So that's deleting an edge. You just throw it out, very simple operation. Now contraction is a little bit different. You take the n vertices and you identify the 2 n vertices and collapse the edge in between. And if you do that for this edge 1 over here, you get this graph. So in terms of matrices, this is what we call the matroid matrix that represents this graph K5. Deletion is throwing out a column, and contraction is making the column a unit vector if needed, and then throwing out the column and the row. So it is, in my opinion, at least, it's easier to do deletions and contractions with matrices than with graphs, although you lose the visualization that you have with graphs. So our goal is to characterize excluded minor classes of graphs and matroids. It's been something that I've worked on for quite a while now. So we'll start with something simple. A graph has no K3 minor if and only if it's a forest, right? That's a K3 is the 3 cycle, and then the graph has to be acyclic. It's a little bit more work, but not that much more work to show that G has no K4 minor if and only if it's a series parallel network. Series parallel network, you start with a loop and add edges, and you subdivide and add edges in parallel. So let me jump to 1963, and it is a slight different, mostly chronological. Every once in a way, it's slightly off chronological, and yeah. So 1963, Dirac proved a simple 3-connected graph has no prism minor if and only if, and he gave a very precise description of the members of the class. So you've got K5 with an edge deleted, the wheels WR, K3P dash with 1 edge, double dash with 2 edges, and triple dash with 3 edges. This is K3P triple dash. So this is a very precise characterization, tells you exactly what the infinite families are. And we only focus on 3-connected graphs. A 3-connected graph is a graph where you need to remove at least 3 vertices to disconnect the graph, because Bixby proved that graphs that are not 3-connected, and here I'm giving you the matroid result. The graph result was actually known before that, although perhaps not articulated until Bixby made it clear. A 2-connected matroid is not 3-connected if and only if it can be written as a 2-sum of proper minors. So this is a 2-sum. Very nice visual in graphs. You can take the 2 edges and just stick it together and delete the edge. So something that's not 3-connected, graphs or matroids, can be decomposed as the 1-sum. The 1-sum is even simpler. You just tack it on at a vertex, or a 2-sum. And that's why we focus just on 3-connected members. So going back a bit, the first excluded minor result is well known. It's the Kuratowski-Wagner planar graph characterization. Kuratowski did it in terms of subdivisions, and then Wagner did it in terms of minors. A graph is planar if and only if it has no K5 or K33 minor. That's K5, that's K33 over there. And a little less well known is Dirac's 1943 characterization. A simple 3-connected graph G has no K33 minor if and only if it is planar or just K5. It's actually K33 that's the main obstruction to planarity. And then we have Wagner's 1937 result also, where he characterized graphs with no K5 minor if and only if it's planar, V8, or a V8 is just the graph place 8 vertices on a cycle and then connect the diagonal vertices. Or G can be obtained as a 3-sum of planar graphs in a V8. So what's a 3-sum? Just like the 2-sum, you stuck a graph across an edge and deleted the edge. A 3-sum is you place flag 2 triangles in the graphs and then place one on top of the other and just delete the edges. So it's a way of decomposing the class. This class, graphs with no K5 minor, is a much larger class than, for example, the class of graphs with no prism minor. So it is difficult to determine precisely what's in the class as in the case of prism minor. However, this is a decomposition result. It's a good enough result. It's what we can get. So you take a larger class and you break it down into smaller, more understandable classes. So then we have the basis of all of these structural results is Tutt proved that a matroid that is matroid is three connected if and only if you can find an element E such that M delete E or M contract E is three connected. And if you, that's a top-down version. If you look at it from the bottom-up version, which you can for graphs and binary matroids, you can start with a wheel and grow your graph by doing edge additions and vertex splits. So from here onwards, I will just give you sort of a broad overview of the results. Now, the main result that started some of this stuff is this genre of excluded minor results in matroids is Seymour's 1980 result on the decomposition of regular matroids. Regular matroids are those with no Fano or Fano dual minor, and that's what they are. And he showed that a matroid is regular if and only if it is graphic, co-graphic, or R10. And the key steps in that process was to show that a three-connected regular matroid is graphic, co-graphic, or has an R10 or R12 minor. R10 is a splitter, and R12 is a 3 decomposer. So that's where we have the splitters and the decomposers and the title of the talk. The thing is, to explain splitters and decomposers properly, we have to do the matroid connectivity function, which is not an easy thing to explain. But the takeaway over here is that you have this function associated to every subset of the ground set of a matroid, and you can define three connected matroids in terms of this function. And a splitter for a minor closed family is a member of the family, minor closed class is a member of the class such that no three connected matroid has N as a proper minor. So this is the well-known splitter theorem here that allows us to construct these matroids in the case of binary and graphic matroids. And this is the definition of 3 decomposer. Think of it as a special graph or matroid in the class such that there is a decomposition that gets carried forward to all the graphs in the class that have it as a minor, graphs or matroids. So this is Seymour's decomposition theorem. It's long, but it's a method for figuring out whether something is a decomposer or not. This is my decomposition theorem, which maybe looks a little bit longer, but it's actually easier to implement, especially if you're using a computer. So it gives us the tools that we need to identify 3 decomposers. And this is the main result. If M is a 3 connected non-regular matroid, so regular matroids have been decomposed. Now we're looking at binary non-regular matroids. And if it has no minor isomorphic to this specific matroid here, S10 or S10 star, then it can be decomposed with a few exceptions. And as a consequence of this result, you can get a nice decomposition of the binary non-regular matroids with no minor isomorphic to the to K33 or K33 dual. So extend that result earlier to binary matroids. And now the big unsolved problem here is, can you do the same for K5? That seems to be a bit harder. Thank you very much. That's it.
Thank you. Any questions, comments?
Too fast?
No, that's a nice talk.
Okay, so can I ask one question?
Yes, yes.
Yes, thank you very much for a very interesting talk. Maybe my question is very nice. So how to define the connectivity of matroids? So in your page 13 slide, you define the three connected matroids by using the connectivity function, right?
Yes.
Yes. So in the previous slides, you also mentioned the connectivity, right? So the definition is same.
It's almost the same. It's not totally the same as graph connectivity. It's almost the same. Yeah. You can think of it as the same, but it's not quite the same. And there are a lot of details that are different, or some details that are different.
Okay, so in the first in the first part in your presentation, how to define the connectivity of matrix? Can you explain again? I'm sorry.
So the connectivity of matroids is defined in terms of the connectivity functions.
Okay.
So for a matroid is a set of elements.
Okay.
You define a function for every subset of elements.
Yes.
As lambda of A is the rank of A plus the rank of the complement minus the rank of the matroid.
Okay.
So that's the connectivity function.
Yes.
So a matroid is 3 connected if lambda of A is at least 2 for all A and its complement of size at least 3. Okay. So if you have so at least the way I think of it is you can compute the connectivity function for your matroid and then just scan through and see that all sets of size 3 satisfy this property. In that case, it is 3 connected. Yeah.
Okay. Thank you very much. Thank you.
Okay, then is there any other questions? So then let us thank the speaker, Sandra.
Thank you.
So the next talk is paper 57.
Yes, sir.
Yes.
Am I audible?
And Borse.
Yes, sir. Am I?
Yeah, you are audible. Yes. Connectivity of the tensor product of graphs and cycles.
Yeah. Sir, is my screen visible?
It's visible.
Yeah. Okay. Good afternoon, all. My name is Amol Sonone. I am working as an assistant professor in mathematics at Ismail Yusuf College, Mumbai. I am working. I am doing my PhD under the guidance of Dr. Vaim Borse. He is a professor in mathematics at Savitribai Phule University. In this presentation, I am going to present entitled "Connectivity of the Tensor Product of Graphs and Cycles." Let's see first definitions of Cartesian product of graph and the tensor product of graphs. See, the Cartesian product of two graphs G and H, denoted by G box H, and is a graph with vertex set Cartesian product of vertex set Cartesian product of vertex sets of G and H, and the vertices U comma X and V comma Y are adjacent if U is equal to V and XY is an edge of H, or X equal to Y and V is an edge of G. So the Cartesian product of K3 and K2 is equal to a graph having six vertices and it is 3 regular. So note that if G is M regular and H is N regular, then the Cartesian product of G and H is N plus N regular. Now let's see the definition of the tensor product of graphs. The tensor product of two graphs G and H, denoted by G cross H, and is a graph with vertex set is same as the vertex set of the Cartesian product of graphs G and H. and the vertices u comma x and v comma y are adjacent if uv is an edge of G and xy is an edge of H. The tensor product of K3 and K2 is a 6 cycle. Note that if G is M regular and H is N regular, then the tensor product of G and H is M into N regular. See, K3 is 2 regular, K2 is 1 regular. So the tensor product is 2 into 1, 2 regular. See, there are a lot of applications of tensor product. I would like to give one. The Head-Smith conjecture. Stephen Head-Smith had conjectured in 1966 that for any two finite graphs G and H, the Kronecker product of tensor product of G and H is equal to minimum of for any finite graph G and H, the chromatic number of tensor product of G and H is equal to minimum of chromatic number of G and chromatic number of H. This result gives the connection between the chromatic number and the tensor product of graphs. And recently in 2019, it is disproved by Sito by giving a counter example. See, now the connectivity of graph G is the minimum number of vertices that need to be removed to disconnect G or reduce it to a vertex, and the connectivity of graph G is denoted by kappa of G. And the connectivity of graphs is an important measure of fault tolerance of networks in parallel computing, and it is closely related to the theory of network flow problems. And the graph G is said to be n connected if that n is less than or equal to the connectivity of graph G. See, if G is M connected and H is N connected, then the Cartesian product of G and H is M plus N connected. But the tensor product of graphs does not behave well with respect to the connectivity, because in 1962, Wissel proved that if G and H are bipartite graphs, then the tensor product of G and H is never connected. Means we can say that even the graphs G and H are connected, their tensor product may be disconnected graph if G and H are bipartite graphs. Let's the history about the tensor product of graphs. In 2009, Gucci and Umar proved that for a bipartite graph G, the connectivity of the tensor product of G and complete graph Kn is equal to minimum of n into connectivity of G and n minus 1 into degree of G. A minimum degree of G. Delta of G means minimum degree of graph G. And they have proved this result for n greater equal 3 and for bipartite graph G. And in the same paper, they have raised the conjecture for non-bipartite graph. And after 2 years, Wang and Zhu settled it for general graphs. And in 2012, Wang and An determined the connectivity of any graph G with K2. And Paul Raj and Agnes in 2013 determined the connectivity of the tensor product of G and complete multipartite graphs under some restrictions on the complete multipartite graph. And Bracer and Spassman in 2008 obtained some upper bounds, actually several upper bounds for the connectivity of the tensor product of G and H. See, in this paper, we construct a graph G tilde from a connected bipartite graph G. We take a connected bipartite graph G and let order per xy be a partition of G and n greater equal to be an integer, be any positive integer, and xi is equal to set of all order pairs x comma I such that x belongs to x, and y suffix I is equal to set of all order pairs y comma I such that y belongs to y for I equal to 0, 1 to up to n minus 1. Let xi and xi dash be graphs isomorphic to our original connected bipartite graph G with bipartitions xi, yi and xi plus 1, yi respectively for I is equal to 0, 1 up to n minus 1, and where the subscripts of xi, xy, hi and h dash are computed modulo n. Let the graph G tilde that we have constructed is equal to union of hi and hi dash, union of hi union hi dash. I ranges from 0 to n minus 1. Then the graph G tilde, the structure of G tilde we can draw like this. And in this paper, we prove that the connectivity of G tilde is equal to minimum of n into connectivity of G and 2 times the minimum degree of G. And using the construction, we got results of the connectivity of tensor product of G and the cycle Cn. The Cn means the cycle of length n. Depending upon whether G is bipartite or non-bipartite and n is even or odd, means Cn is a cycle of even length or odd length. We have divided this into some parts. First, if G is bipartite graph and n is an odd integer greater or equal 3, then the connectivity of tensor product of G and Cn is equal to minimum of n into connectivity of G and 2 times minimum degree of G. If G is bipartite graph and n is an even integer greater or equal 4, see here if G is bipartite and if n is greater or equal 4, then and even, then Cn is a even cycle, means it is bipartite graph. And we have seen that the tensor product of bipartite graph is a disconnected graph, means if here we are taking G is bipartite graph and Cn is even cycle, means it is also bipartite. So the tensor product of G and Cn is disconnected graph, and we prove that it has 2 isomorphic components, each with connectivity minimum of n by 2 into connectivity of G and 2 times minimum degree of G. If G is non-bipartite graph and n is an even integer greater or equal 4, then the tensor product of G and Cn is connected and its connectivity is equal to minimum of n by 2 into connectivity of G cross K2 and 2 times minimum degree of G. And last case, if G is non-bipartite graph and n is odd integer greater or equal 5, then we proved that then the connectivity of G cross Cn is greater than or equal to minimum of n minus 1 by 2 connectivity of G cross K2 and 2 times minimum degree of G, and less than or equal to minimum of m plus 1 by 2 into connectivity of G cross K2 and 2 times minimum degree of G. And in this paper we also prove that if H is the tensor product of k odd cycles, tensor product of k odd cycles, means here H is 2 raised to k regular graph, and here we prove that the connectivity of tensor product of H and K2 is equal to 2 raised to k. See, since H is 2 raised to k regular and K2 is 1 regular, tensor product of H and K2 is 2 raised to k regular, and here we proved that the connectivity of tensor product of H and K2 is also 2 raised to k. And as a consequences of the result we have seen earlier and this result, we proved that the connectivity of the tensor product of k cycles, of which at most one cycle is even, See, here we are taking at most one cycle is even, because if you take two even cycles, then the connectivity of tensor product of that k cycles is disconnected graph and its connectivity is 0. Therefore, here we are taking that we are finding the connectivity of tensor product of k cycles, of which at most one cycle is even. If one cycle is even, that the tensor product of k cycles is connected graph, and we proved that its connectivity is exactly is 2 raised to k. These are the main results of the paper. These are the references I use. Thank you.
Okay, thank you, Sonavane. Is there any questions, comments? No questions? Then let us thank Amol Sonavane once again. Speaker.
Thank you, sir.
So we have a last presentation, last talk by contribution paper 64, Amruta Shinde and Yashwant Bose, disjoint cycles through prescribed vertices in multidimensional tori.
Yes, sir.
Please. So Amruta Shinde will be presenting, right?
Yes, sir. Yes. So, sir, is my presentation is visible?
Yes, yes.
Okay. So, hello everyone. This is Amruta Shinde. I am from Center for Advanced Studies in Mathematics, Department of Mathematics, Savitribai Phule, Pune University. Today I'm going to present a paper on disjoint cycles through prescribed vertices in multidimensional tori. This is a joint work with my PhD supervisor, Dr. Y.M. Borse. So first of all, let's start with Cartesian product of two graphs, G and H, which is also a graph with a vertex set V. It consists of ordered pair UV, where U belongs to a vertex of G and V is a vertex of H. And the edge set of Cartesian product of G and H is order pair two order paired U1 V1 and U2 V2. These two ordered pairs are adjacent if and only if U1 and U2 is an edge of graph G and V1 equal to V2, or V1 and V2 are edge of graph H and U1 equal to U2. So the Cartesian product of n copies of K2, where K2 is a complete graph on two vertices, is called an n-dimensional hypercube. Similarly, the Cartesian product of n cycles is called an n-dimensional tori, and if the length of each cycle is k, then it is called k-array n-cube. The hypercube, tori, and k-array n-cube are extensively used in the interconnection networks. Also, the cycle also are popular networks due to their simple structures and low degree. The problem of finding various length cycles in a graph is called a pancyclic problem. There are various types of pancyclic problem. One such problem is finding a Hamiltonian cycle in a graph. There are other generalization of Hamiltonian cycle. One is such that finding a k-vertex disjoint cycles which also span the given graph. In 1963, Corradi and Hejnal proved that if G is a graph of order greater equal 3k and minimum degree of graph G is greater equal to k, then the graph contains k-vertex disjoint cycles. Then some of the problems of this vertex disjoint cycles contain specified vertices or the specified edges. So in the 2009, Gao, Yan and Li considered the vertex disjoint cycles containing prescribed vertices in a bipartite graph. Then this result is improved by Zhang, Yan and Jiang. And in 2013, Lin, Tana, Zhu and Kohn in the paper of disjoint cycles in hypercubes with prescribed vertices in each cycle, published in Discrete Applied Math, gave the following theorem. The hypercube is spanning R cyclable whenever R is less than or equal to n minus 1. Similar result for crossed cube, which is a variation of hypercube, is given by Kung et al. In 2016. So one can find a very good survey papers on this topic by Gold and Chiba Yamashita. So here we are now giving the formal definition of spanning R cyclability of a graph. A graph G is a spanning R cyclable if for any given R vertices V1, V2, Vr, there exist R vertex disjoint cycles Z1, Z2, Zr in G such that the union of this cycle spans the whole graph G and each cycle Zi contains a vertex Vi for each I where I runs from 1 to R. So we explore the spanning R cyclability of the Cartesian product of n cycles. So here for take first example, Cartesian product of two cycles C4 and C3. And if we choose 4 vertices V1, V2, V3, V4. Now our target is to find 4 vertex disjoint cycles, each contain exactly one of this Vi, and the whole cycle collection of the cycles should span this whole C4 cross C3 graph, and this cycle should be vertex disjoint. So if now here we can see that this vertex V1 is adjacent to V2, V3 and V4. Therefore, in the graph C4 cross C3, each vertices has 4 degree. So therefore, we can see that this V1 has only one unprescribed vertex. So therefore, if you want to find a cycle passing through V1, there is only one vertex is available. Therefore, there does not exist a cycle which contains this V1. Therefore, we conclude that the number of prescribed vertices must be strictly less than the degree of the torus. So formally, we give the lemma for positive integers n and r. Every n-dimensional torus is not spanning R cyclable if R is greater than or equal to 2n. So again take example 2, the Cartesian product of C3 with C3. Now from the above conclusion, we know that the number of prescribed vertices should be less than 4. Therefore, let's take 3 vertices, prescribed vertices U, V and W. Now we again want to find 3 vertex disjoint cycles such that each contains U, other cycle contains V, and the third cycle contains W. So here take this Cu cycle which contains U. Now if you want to find cycle containing W, now here the cycle containing W should not intersect with Cu, nor it should contain V. So only possibility of this CW cycle is this C4 cycle. So here we can see that now if you want to find a cycle containing V, but there are only 2 vertices, so this is not possible. So from this example, we can conclude that the torus C3 cross C3 is not spanning 3 cyclable. So from this, we state our main theorem for positive integers n and r, with r is less than or equal to 2n minus 1, and n-dimensional torus is not isomorphic to C3 cross C3 is spanning R cyclable. The immediate corollary from our theorem is that K array n cube is not isomorphic to C3 cross C3, it's spanning R cyclable. Further, if K equal to 4, then the 4 array n cube is the Cartesian product of n copies of 4 cycle. Thus, the result is true for even dimensional hypercube. So now we give the proof of our main result. The proof follows by induction on n. Let's take n equal to 1. So here we can see that r is less than or equal to 1. So in this case, we can choose only one prescribed vertices, but the cycle C, take any vertices from the cycle C, we can only get the cycle C. So here the result trivially holds for n equal to 1. So now let's assume that the result holds for n minus 1. Let F be the set of prescribed vertices with cardinality R, which is less than or equal to 2n minus 1. Now G is the Cartesian product of n cycles, which are CM1, CM2 and CMN. So here G can be also written as H times CMN, where H is the Cartesian product of n minus 1 cycles. So again here we can write as G as a mn copies of H, and it is a collection of HI with the perfect matching between two consecutive HIs. So our target is, now we have to obtain a collection of cycles C of R vertex disjoint cycles that together span the graph G, and each cycle contains exactly one vertex from the set F. So if each HI contains at least one of the vertices of F, then the cardinality of these prescribed vertices should be less than or equal to 2n minus 3. But this, if this is the case, then by induction the result follows. Now suppose that there are some HIs which does not contain any prescribed vertices. So in this case, let's suppose that H1 contains the maximum number of prescribed vertices. So depending upon the position of F, we have the following three cases. So first case is that R1 is less than or equal to 2n minus 3. That is, H1 contains at most 2n minus 3 prescribed vertices. So here we can see that H1 has this prescribed vertices V1, V2, VR1. And then by induction, we have this C1, C2, so on up to CR1 cycles. And these other copies, for the time being, let's say it does not contain any prescribed vertices. So H2, H3 up to HI does not contain any prescribed vertices. But these HI copies, which are isomorphic, therefore this cycle C1, C2, CR1, this will be present in H2, H3 up to HI. So here we can see that these cycles, now we know that there is a perfect matching between H1, H2, H3, H2 and H3 and so on. So we can form this graph. This will be C1 cross this path, Pi. So we know that Cartesian product of cycle with path has a Hamiltonian cycle. So thus we get this cycle which contains this one prescribed vertices. So for each cycles in H1, we get this bigger cycle. So therefore the collection of these new cycles C1 dash, C2 dash, CR1 dash spans whole H1, H2, H3 up to HI. And each cycle contains exactly one prescribed vertices. So thus, now we have covered all these HI copies. Now if let's suppose that HI plus 1 contains remaining prescribed vertices. So by induction, we know that this there exists cycle D1 and D2, which contains prescribed vertices and spans HI plus 1 copy. So here the remaining copies of HIs that does not contain any prescribed vertices. Therefore, following the same technique as used in this red cycles, we can cover this whole graph G, thus without increasing the number of cycles. Therefore, this case is complete. Now, if we see that H1 contains 2n minus 2 prescribed vertices. So therefore, in this case, there exists one cycle which contains exactly 2 prescribed vertices. But so to prove our claim, we need to cut these cycles into 2 parts, and each part contains these prescribed vertices. So again, using this remaining copies of H2, HIs, we get these cycles. So again, there is only one prescribed vertices is remaining. So that would be present in the remaining copy. And again, following the same technique, we get the result. So the last case is if H1 contains 2n minus 1 prescribed vertices. So in this case, there will be 2 types, that 2 cycles contains 2 vertices exactly, prescribed vertices each. So again, we break these two cycles and again form the bigger cycle to get our required collection of cycles. And the case, there is one case that the cycle C1 contains 3 prescribed vertices. So here again, we break the cycle and using the path and the result of Cartesian product of path with path contains a Hamiltonian cycle. So this result, so here we get all the cycles which span the whole graph G. So this proves our claim. So these are the references which I used in my paper.
Okay.
Yeah.
So thank you for your nice presentation.
Yeah, thank you, sir.
Yeah, you explained the proofs really well. Is there any questions? Any questions? Or comments? So then let us thank the speaker. And that is the end of the session. We thank all the speakers
Thank you,
who
sir.
have done this session once again. Thank you. Thank you very much.
Hello.
Yes.
Yes. Thank you, Professor Manoj. We will disperse now to join for the plenary talk by Neil Koblitz at 17:30, 5:30.
Thank you.
We have break for more than 30 minutes.